So, the plan for today is to or the plan for this week rather is to look at the generalization of the quantum Fourier transform for Zn. So far remember we have seen this for Z2 to the n, Z2 to the small n, right. And now what we will see is, we will see how to generalize this idea to a different space Zn with capital N. In general, we will think of n as 2 to the small n for some small n, right. And what we will see is that once we generalize the quantum Fourier transform to this new space, we can similarly generalize Simon's algorithm which we saw before, right, to this new space, and this will very quickly lead us to Shor's algorithm. So, this is a two-step process by which we will see Shor's algorithm. We are going to see how Simon's algorithm over Zn essentially helps us to find the period of a periodic function, and then we will see how this applies to finding discrete log and factors of a large number. So, there are a lot of subtleties along the way. In the class, of course, we will not have time to go into every little detail of all the proofs, but I will try to emphasize all the ideas as much as I can, and for more details we will look at notes and scribes. So, let us get started. So, first of all let's sort of do a quick review of QFT over the space that we did see, which is Z2n. Okay. And this, if you remember, what we were doing was we were taking some function, we were calling it g, I mean of course you can call it what you want. So, take a function g, think of it as a vector, right, its truth table, for instance, you can think of the truth table representation of a function, and we saw that you can always express a function along a standard basis, right, which is just well, we already saw. So, we take the indicator functions and take the function value times the basis vector and sum it over all basis vectors. And what we saw essentially was that instead of using the standard basis, we can use what is called a parity basis. Okay. So, let me just very quickly remind you. So, we'll see how really the QFT over the new space is also just going to translate these ideas. So, which is why I think it's useful for us to very quickly go through this again. So, if you remember, we had a basis of what we were calling parity functions. Okay, and we were defining these in this way. Now, here if you remember, so this this is inner product mod 2. Okay, so we are looking at binary vectors of length small n, and we are defining these basis functions in this way. In particular, what we also discussed is that these chi functions, they are what are called as characters on Z2n. So, maybe I did not spend too much time on this, but today we will talk about what characters are, and this is going to help us to generalize the idea and not be so tied down to this one particular space. Okay, so good. So, these were our basis functions, and now using this, what we were able to do was we were able to represent g as some summation of g hat gamma. So, gamma is over Z2n, g hat gamma chi gamma, right. Everyone remembers this. Okay, so, this was our Fourier transform. Okay, so, this is the this is the whole function. Of course, you can specialize this and find its evaluation on a particular point. I am writing it as the whole vector. Okay, so, this is what we saw. And now let us sort of dig a little bit deeper into this notion of characters. So, we already saw all the properties that make these functions as characters. We will just be a little more formal now. So, let us look at a definition. let C star denote non-zero complex numbers. And let G be a group with operation denoted by asterisk. So, note here that I am taking an abstract view of this operation. Okay. So, it does not mean that this is multiplication, just that a group has a certain operation and we will just denote it by asterisk. Okay. So, a character in G or a character on G rather is a function chi going from G to C star satisfying this property. Okay. So, chi of G asterisk H is equal to chi of G times chi of H. So, what this means is that this chi is a homomorphism, what is called a homomorphism, okay, from G to C star. Okay. So, this is the basic definition of a character, and this is not difficult to see in our example of Z2n. Okay. So, let us in particular spend a few minutes looking at some of the properties of characters that we have already used. Okay. So, we are just going to highlight some properties that we have already used. So, one is that chi 0 of anything is just going to be 1, right. So, if it is minus 1 to the gamma x and I am taking gamma as 0, then obviously this will just give me 1. So, this is just a basic property. So, the second property is the following. So, if I take the expectation over all x of chi gamma x, and here I am thinking of gamma not being equal to 0. Can you tell me what is this expected value? We have seen this, it is 0, very good. And yeah, we have seen this, I will not spend more time on it. A third property is chi alpha of x is the same as chi x of alpha. This follows just by the definition, but even though this is true, we generally we write it in the way that is natural. So, we generally write chi gamma x or chi alpha x, whatever. So, the two are interchangeable, but it makes sense to segment in the most natural way. Okay. So, anyway, this is just a simple property. Very good. Now, an important property that we saw last time was that how do you compute the Fourier coefficient, right. So, for chi gamma, what is the Fourier coefficient when I write G along this basis? Very good, that is exactly right. So, Akhil said it exactly right. So, this is expectation over x chi gamma x Gx. Okay. And more generally, a nice way to see this is actually this is the inner product of chi gamma and G. So, this is a nice way to remember what these coefficients look like. Whenever I do a change of basis, right, I go from one orthonormal basis to another, I can always compute the coefficients in this way. Alright. So, this is at least to me it is easier to remember it in this way than this expectation. Okay. And then another property which we used is this, right. So, chi of gamma plus sigma x is equal to chi gamma x, chi sigma x. Okay, and this is of course what we want for it to be a character, right. This is the homomorphism property. So, the Fourier transform is the unitary transformation that takes any function f, or let me use g since we are using that takes any function g to its representation with respect to this basis, right. So, in particular we saw that 1 over root n summation over x g x x, this is the representation using the standard basis, is this can be written as equal to summation over gamma g hat gamma gamma. Okay. So, this is so far just a recap. So, now what we will do is we will start generalizing this. Another quick reminder is that if you remember, you know, for any x, so I mean so far we have talked of these functions, but if I think of any set of qubits, right, then when I compute the Fourier transform, then what do I get? I can write this x as 1 over square root n summation over gamma minus 1 gamma x chi gamma. I hope that everybody remembers this. Okay, so if you okay, just maybe for the sake of completeness, so you know I can write x as a function. Okay, so let me maybe just do that. So if I let g x of y as square root n when y is equal to x and as 0 otherwise, right, then what does g x look like? So this is the vector representation will look like this, right. So summation over y g x y y, and this is nothing but x. Okay. So, yeah, so in general we think of functions, but of course this will capture just general states as well. And we saw multiple examples of how to use this Fourier transform. So now let us generalize all these ideas to Zn. Okay. So let us try to arrive at what the characters should look like. Okay. So now consider Zn. Okay. So let us try to figure out, as I said, what characters this should have. So one of the things that we said about characters is that, you know, it should satisfy this homomorphism property, right. So chi of x is nothing but chi of x plus 0, right, which should be by homomorphism chi of x chi of 0. Okay. And this implies that what does this imply? This implies that chi of 0 is 1. Okay. Okay, good. Now similarly, so this is one simple observation. Now similarly, if I have, you know, x plus x, right, k times, then this is nothing but chi of x the whole to the k, right. And now if you know k is equal to n, then what does this imply? I claim this, I claim that this means that chi of x to the n is equal to 1. Why is that? No, I mean yes, but therefore, so x plus x, you know, n times, that is n times x, so that becomes 0, and then chi of 0 is 1, so that is why. Okay. So, chi of x to the n is nothing but chi of nx, which is nothing but chi of 0, which is 1. Okay. So, this means that chi of x to the n is equal to 1. So, this literally means that chi of x is an nth root of unity, right. This is exactly by definition. And since chi of k is, you know, chi of 1 to the k, we have that chi is completely determined by its value on 1. Okay. So, now we know that chi of 1 is an nth root of unity, right. So, that means that we can write chi of 1 as omega to the gamma, where omega is a primitive nth root of unity. So, omega is what? E to the 2 pi I over n, right. This is a primitive nth root of unity, and gamma is just something in Zn. So, therefore, now what do I get? I get that chi of x, right, which is chi of 1 to the x, which is omega to the gamma to the x, is equal to omega to the gamma x. And now note that here these are integers in Zn, right. So, this is no longer an inner product, this is just integer multiplication. It is all clear so far, right. So, it is exactly what we have seen before, but we are just generalizing the space now, right, and we are getting some very natural properties. So, the fact that chi of 1 is a root, is an nth root of unity, right. This is one of the important things that we saw. And this implies that, so if I take chi of, okay, in fact let me do this a little more carefully. So, now let me define chi gamma Zn to C as chi gamma of x is equal to omega to the gamma x. Okay. Then chi gamma x plus y, I claim, is chi gamma x chi gamma y. Does everyone agree? Okay. So, we can conclude that the set Actually, we cannot conclude yet. Maybe we will claim that the set chi gamma for gamma in Zn forms an orthonormal basis. And as you can imagine, so now when we apply our Fourier transform, these are the basis functions we will use, and we will figure out what are the coefficients for these basis functions. So, you know, establishing that these form a basis is not hard. So, you know, once again let us establish some of the properties of these characters, and we will see that these form a basis. Okay. So, one thing you can immediately see is that there is the right number of them, right. So, we have as many as we need. So, we just need to show orthonormality, we will show that. So, let us establish some properties. So, chi of 0 is again 1 by definition. Okay. Another nice thing is that, you know, this expectation of x when sampled over Zn chi gamma x, okay, this also turns out to be 0 for gamma not equal to 0. And this actually maybe this is worth writing. So, this follows, so remember we are looking at expectation over x chi gamma x. Okay. So, this follows from the definition of expectation and chi gamma. So, this is summation 1 over n I going from 0 to n minus 1 omega to the gamma or x going from 0 to n minus 1 omega to the gamma x, right. This as you know works out to omega to the gamma n minus 1 divided by omega to the gamma minus 1. So, everybody would have seen this before, right. So, this is just what the summation turns out to be. It is very easy to prove, and since omega to the n is 1, this is equal to 0. Is it fine? Okay. So, this is again this is analogous to what we saw before. So, that is why we were looking at those properties, right. So, the expectation over x chi gamma of x was 0 even earlier, and the same thing holds now. Okay. Okay. What other properties do we have? So, the third property also holds. Okay. So, chi alpha of x is the same as chi x of alpha. This is very easy to see just by definition. Okay, and also chi sigma of x, chi gamma of x is once again equal to chi sigma plus gamma of x. So, again this follows just by definition. All right. And now we have one more definition, because not definition, we have one more property which will be very useful for us, which is to look at the conjugate of this. Okay. So, what is the conjugate of chi gamma x? So, this is equal to chi minus gamma x, I claim, which is the same as chi gamma minus x. Can you tell me why this is true? So, chi gamma x conjugate is what? So, it is omega to the gamma x, the whole conjugate, right, which is nothing but omega to the minus gamma x. Does everybody agree with this, right? So, just think of omega is e to the 2 pi I by n, write it as you know cos plus I sine, and then the conjugate will flip the sign, right. So, you will get this, and this will give you what you need. Okay, so now equipped with these properties, we can immediately conclude that these form an orthonormal basis, right.